In the silent, vast cosmos lie the ghosts of long-dead stars. These aren't just cosmic crime scenes. They're the universe's most violent events, and we're on the case. We're forensic astronomers, sifting through stellar wreckage with incredible tech, decoding those final fiery moments. The secrets we're uncovering? They reveal the very origins of our universe and ourselves. Every supernova leaves a cosmic calling card, an expanding cloud of shredded gas, rich with brand new elements. The catch? The star itself vanished millennia ago. All that's left is shrapnel, still screaming outward at millions of kilometers an hour. Imagine arriving at a burnt-out building after the fire department has left. The walls are gone, but the scorch marks, broken glass, melted wires, they tell a story if you know how to read them. Astronomers do exactly that. We scan the sky across the entire spectrum: X-rays, infrared, radio, even those faint whispers of light echoes. Light that left the scene centuries ago, bounced off interstellar dust, and is only now reaching Earth. Each wavelength offers unique evidence. X-rays reveal million-degree shock fronts. Infrared picks up warm dust packed with freshly forged iron and silicon. Gamma rays betray radioactive titanium and cobalt, the lingering fingerprint of nucleosynthesis that happened in mere seconds. Piece these clues together, and you can reconstruct the blast's energy, the progenitor star's mass, and sometimes even the type of supernova that did the deed. Our most powerful forensic tool? NASA's Chandra X-ray Observatory. Its mirrors are so smooth that scaled to a U.S. state, the biggest bump would be just a few centimeters high. That precision lets us map ejecta temperature and velocity to fractions of an arc second. Pair Chandra's data with ESA's XMM Newton, and you get spectral lines sharp enough to measure Doppler shifts of just a few hundred kilometers per second, practically slow motion in cosmic terms. This helps separate the star's guts from interstellar muck. Meanwhile, integral and ground-based Cherenkov arrays like HESS hunt for gamma-ray lines. Spotting titanium-44 at 68 or 78 keV tells us how much radioactive fuel was cooked up and how energetic the explosion was. High titanium to iron ratio, core collapse, low, white dwarf thermonuclear detonation. It's like measuring gunpowder residue to decide between a firecracker and dynamite. Finally, integral field spectrographs like MUSE on the Very Large Telescope provide a 3D data cube, 2 dimensions of sky plus 1 for wavelength. Light echoes? They're the universe's own CCTV footage. Photons from a supernova blast past interstellar dust, scattering some toward Earth, centuries later. We aim a telescope at that dust, collect that ancient light, and take a spectrum as if the explosion were happening right now. For Cassiopeia A, astronomers recovered the original ultraviolet flash, confirming the star shed a thick cloak of carbon-rich gas just before it blew. Something no 17th century observer could have recorded. This trick works for historical supernovae too. Light from the 185 AD event that created RCW 86 still bounces around the Milky Way. Echo spectra reveal silicon but little hydrogen, the unmistakable hallmark of a Type Ia explosion. Combine that with the remnant's sheer size and surrounding cavity, and we understand. The white dwarf tore through a low-density bubble carved by its own wind, letting ejecta race outward unimpeded. Without those centuries-delayed photons, we'd never have solved why RCW 86 is so enormous for its young age. Modern simulations let us replay a star's final act in super slow motion. A 10 million degree shock races down its interior in milliseconds. When it hits the surface, the star's outer envelope is catapulted outward at up to 10% the speed of light. Meanwhile, the core collapses into a neutron star or black hole, unleashing more energy in 1 second than our sun will emit in 10 billion years. That energy fuses iron into heavier elements, gold, platinum, uranium, then flings them violently into space. By comparing observed elemental ratios to our simulations, we figure out if the star was a chubby red supergiant 20 times the Sun's mass, or a svelte white dwarf no bigger than Earth. Take Tycho's remnant. Its iron-to-silicon ratio almost perfectly matches a white dwarf detonation, helping us categorize it centuries after the blast lit up Danish skies. We can even spot asymmetry. If the iron glow is stronger on one side, it tells us the explosion itself was lopsided, a phenomenon 3D models predict when nuclear burning starts off-center inside a white dwarf. These subtle details matter because a Type Ia's energy feeds directly into our measurements of cosmic expansion, impacting the debate about dark energy. Think about this. Every carbon, oxygen, calcium atom in you, all forged in a star, delivered by a supernova. Studying this cosmic debris teaches us not just how stars die, but how the raw materials for planets and life came to be. The iron in your blood needed a stellar furnace hotter than 1 billion degrees. The gold in that wedding band formed in the neutron-rich chaos of a collapsing stellar core. We aren't just observers, we are the cosmos's children. Supernova archaeology also calibrates the universe's distance scale. Type Ia supernovae blaze with a standard luminosity. By refining their true brightness through remnant study, we tighten our cosmic ruler. Sharper distances mean sharper estimates of dark energy's strength, shaping predictions of how the universe will end. Big freeze, big rip, or stranger. Finally, these remnants act as nature's particle accelerators. Shock waves rip through magnetic fields, boosting protons to energies far beyond CERN's dreams. These cosmic rays pepper Earth, subtly mutate DNA, and possibly seeded lightning in our early atmosphere. Solving a dead star's forensic puzzle informs everything from biology to climate science. If you're enjoying this cosmic investigation, tap that subscribe button and ring the bell. We drop more cold case star files every month. And hey, let me know in the comments, which unsolved astronomical mystery keeps you up at night? The 1181 AD guest star? The missing neutron star in Supernova 1987A? Your question might become our next deep dive. Let's put our toolkit to work on a real case, RCW86. This remnant is from the supernova recorded by Chinese astronomers in 185 AD. For decades, we assumed it was core collapse due to its immense size, roughly twice the angular diameter of the full moon. Yet X-ray spectra stubbornly showed iron lines typical of a Type Ia. This paradox puzzled theorists until multi-wavelength mapping cracked the case. Infrared data from Spitzer revealed a vast, almost empty cavity around the explosion site. The progenitor system, likely a white dwarf orbiting a normal star, had been spitting out fierce wind for millennia, carving a bubble tens of light years wide. When that white dwarf breached the Chandrasekhar limit and detonated, the ejecta slammed into this pre-existing bubble and kept going, racing through the low-density void like shrapnel down an empty hallway. That explains its huge size without needing an unrealistic age. Chandra images add another twist. The forward shock still bumps into denser gas clumps, lighting up like a neon tube wherever the magnetic field pinches. Measuring shock movement between 2007 and 2020 images, we clock expansion speeds up to 1,100 kilometers per second. Plug those numbers into hydrodynamic models, and you get an explosion energy of roughly 10 to the 51st ergs, perfectly typical for a Type Ia supernova. This confirms RCW86 belongs in the white dwarf column despite its giant stature. The next decade in this field, it'll feel like handing Sherlock Holmes a DNA lab. Upcoming missions like X-RISM will capture spectra with microcalorimeters, resolving shock velocities to an incredible 30 kilometers per second. They'll detect trace elements like chromium and manganese, crucial signals for Type Ia blast ignition. On the ground, the extremely large telescope's 39-meter mirror will resolve individual filaments in remnants across the local group, letting us apply our forensic toolkit to extragalactic supernovae for the first time. Meanwhile, machine learning algorithms are already trawling archival data, hunting for missed light echoes. One candidate, tentatively linked to the 1054 Crab event, was recently spotted in a 1986 photographic plate. If confirmed, we could obtain a spectrum of that original explosion and watch how the pulsar's wind has re-energized the cloud in real time. And when the next nearby supernova finally goes off, statistically overdue in our own galaxy, we'll have neutrino detectors and gravitational wave observatories online. These messengers leave the scene hours before light escapes, giving us a crucial heads-up to slew every telescope in the sky and capture the cosmic crime as it happens, live. So next time you gaze at the night sky, remember, every twinkle is a story, and every dark patch between the stars might hide the cooled ashes of a cataclysm that made you possible. Supernova archaeology is more than a clever phrase. It's how we piece together our cosmic ancestry. By reading heavy element fingerprints, timing ancient light echoes, and replaying a star's final frames in supercomputers, we transform destruction into knowledge, silence into narrative. We started with ghosts and crime scenes, but we end with connection. The calcium in your bones once glowed at a remote sun's heart. The iron in your blood surged through its atmosphere before that sun ripped itself apart and seeded the cloud that became our solar system. We aren't separate from the cosmos. We are its memory, its investigators, and its children. Stay curious, keep asking questions, and never stop looking up. Thanks for joining this deep dive into supernova archaeology. For more cosmic investigations, smash that subscribe button. Check out our playlist on how neutron stars are born. Share this video with the stargazer in your life, and as always, keep looking up.